14.2, limits and continuity. I would sing Take It to the Limit one more time by the Eagles, but if I did that, then you guys would say I was a bad singer, and probably YouTube would copyright strike my video, which also be also awful. Okay, so I'm like, this video is going to be viewed by so few people. What would it matter if I got a little crazy, right? Okay, I just want you guys to recall from Calc 1 and also Calc 2, because you guys did limits in Calc 2 as well, what happened when you had just one independent variable in 2D. As you approached, let's see, here must be x is 1 from this drawing. So as I approach x is 1 from the left and from the right, there is just one path that I'm going on to find my height. In this case, my height is y. And so as my inputs approach, the value for my input approaches x is 1, right? My output is approaching 2. And even if I have a hole in the graph, and this is where it's actually defined, right? Where when x is 1, y is 3, that's still the limit. And there's just one path that gets me there. The reason I'm talking about one path is there's going to be more than one path when we start thinking about surfaces in 3D. And so anyway, so all of these things, the limit exists and it's 2. The limit exists and it's 2. The limit exists and it's 2. Except for this one, because as I approach from, looks like x is 2, as I approach x is 2 from the left, my output is approaching 1, but from the right, my output is approaching, is that 4? Approaching 4. Okay, so as I'm going along this one path, right, this path right here is on the x-axis, my heights are approaching different values. So there was just one path to our point. And so our point here being x is 2. And it was to go along the x-axis. Finding the limit meant walking that path from the left and from the right. And if our output from the left and our right agreed, then it was our limit. But in 3D, it's a little bit more complicated. There are infinitely many paths to each point, and you can't possibly go and prove that all of them have the same height. It's not possible to do that. So to prove the limit exists, we must prove that along all of the infinitely many paths we approach the same limit. So we're going to have to do that besides just checking them all, because if there's infinitely many, you're not going to be able to check them all. So this is kind of the idea, is that if I'm trying to approach this point and then look at the height, right, and compare the height, as I can go, this looks like I'm going to the point along something that's parallel to the y-axis, here parallel to the x-axis, it looks like. And here I'm taking some kind of a curve to it. So to that point. So there's just 3, and you can imagine there's infinitely many that could go to that point. And we're asking, is the output, which is z value, the same for all of those different as I get closer and closer to that point? So I have to have something, and so now today I have made, I don't know if you're going to call it trail mix, with just Cheerios and a few M&Ms. No, those are not M&Ms. Those are chocolate chips. But those are to help me get from page to page today. I didn't have to have one right now because then I would be crunching those Cheerios. And so I wouldn't be a mathematician if I didn't try to lay a little delta and epsilon on you every now and then. But they say let f be a function of 2 variables whose domain D includes points very close, arbitrary close to AB. Then we say the limit of f at xy as xy approaches AB is L. And how we would denote that is like this. And that's something that we see. My quacker is quacking. And for every number epsilon greater than 0, there corresponds a number delta greater than 0, such that if xy is an element of the domain, and we have, this should have been y. I didn't notice that typo last semester, and I got this from somebody else, so it was their typo. I got it from someone else when I was too tired to type, is what I got. So as we get closer, basically all they're saying is that we're putting a value on how close we are. So if you're closer than delta, then your function and your limit, when you subtract them and take the absolute value of it, they're closer together than epsilon. And so that's the only story there. And so in our book in Calc 1, I would say very, 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 very close is what I would say, very close. So in other words, and this is just saying the value of f at xy, so that's our output, approaches our limit as our inputs approach this point along any path within the domain of f. Techniques for finding limits at a point A, B include the usual things that you learned in Calc 1 and Calc 2. And substitution, factoring, etc., multiplying by the conjugate, all those kind of things. And another story is that I wish I wouldn't have written it exactly this way, because substitution could get you 0, 0 here too, and then you could factor it or multiply by the conjugate, and then it turn out to be the limit somehow. But one thing is if you suspect that the limit doesn't exist, is if you can show that it's different for two paths, then you can show that the limit doesn't exist. Now, checking two paths and having them be the same is not helpful, because you have to show that it's true for infinitely many paths. But if you can show that it's different from two, then you can show that the limit doesn't exist. So that's what this story was in here, and I wish I would have written it a little bit differently. Now that I'm reading it, it made perfectly good sense when I got it from my friend Professor Leonard. But okay, so things to consider when picking paths. And we're going to practice this, don't worry. So, and when you start picking paths is when you are starting to think that maybe the limit doesn't exist, or you're not sure exactly how to go. Then you can pick a few paths, and if you're getting all the same, then you know, well, maybe the limit does exist. Let me see if I can prove it. So be certain that the point AB is actually on your path. Try to use paths to make the degree of the numerator and the denominator equal. And then some other things for proving limits are our friend, the squeeze theorem. And I'm not sure that you converted things to polar coordinates in Calc 2 in order to find limits. It's been so long, I don't remember. But converting to polar coordinates, we'll give a try to that as well. Okay, so it says here, find the limit if it exists, or show that the limit doesn't exist. So if I try to plug in here, x is 7. 7, to have the eraser, because I was going to put -7. So I'm plugging in x is 7 and y is -1. Then in the numerator, I get 0, which is fine. You can get 0 in the numerator. But what's not okay is that I get 0 in the denominator. So I have 0 over 0, which is an indeterminate form. And so it could be that the limit doesn't exist. That's a possibility. It also could be that the limit does exist and that I could find it by using one of the techniques that I learned in, I think mostly in Calc 1, like, factoring or whatever have you. And so if I give a try to factoring, see how in the numerator has a common factor of x, then I could be finding here the limit. I don't want to write this too many times. Trust me. It's hard to fit that underneath the limit sign, like you could fit the other underneath the limit sign. But if I factor out an x, and I get here x plus 7y divided by x plus 7y, and then the x plus 7y's cancel out, right? So this is the same as finding the limit, as because you can have a little hole in the graph, that's okay. As we go to 7, -1 here of x, and so x is 7, and so this is equal to 7. And then I put this picture here, and I'm going to go to my computer view, because on my computer view I have that here as well. And so, and you can rotate it around. So I put that in. And so when we come here in the, and we're approaching, and I'm going to put this point here, x is 7, y is -1. Ooh, how did I do that? How did I get that as a subscript? Do you ever wonder how you do something? How did I do that? I don't even know. And z is 0. It's already assuming z is 0. But there's that point right there. I'm going to put that in, enter it, and it's going to call it point A there. And so here's the story is that if we go straight up and we hit our plane, we're going to be hitting our plane at a height of 7. So I'm going to put that in here as an ordered pair. 7, comma, -1, comma, 7. I need to, it doesn't look like it's on my plane, does it? And that sometimes happens when you use these programs. So I had to make my plane a little bit bigger because that plane goes on forever. And so you can definitely see that it's hitting that plane, and you can see that it's straight. It's going straight up to there, and it's hitting, that's where it's hitting that plane. Now that would be a little hole in the plane because that would be a value that would make the denominator 0. But no matter what path I go on, I'm getting closer and closer from to that point, no matter which path that I go on. Anyway, so that's kind of the story there, what we found. Let me see if I can go back to paper view. It's very tricky because I have to have 2 monitors, and I'm not very good at using 2 monitors. Okay, so we did a lovely job on that one. Here's another one. Find the limit if it exists, or show that the limit doesn't exist. And I put the +2 there just so that when we look at the drawing of it, it will get off of the XY axis because this one was so close to it. So the +2 just lifted it up a little bit so that we could see. And so if you're wanting to examine how to test paths, and what you're trying for when you do paths is you're trying to find a contradiction so that you can say the limit doesn't exist. These are some of our favorite paths. There's other paths as well that you could use, but these are some of our favorites. And so if you use this path, x equals 0, then what you're going along is the y-axis is what you're going along. So you're getting the y-axis on here, on this picture that I have here, is in green. So going along the y-axis. So as I go along the y-axis and get close to y, and I'm getting closer and closer to y is 0, right? If your x is 0, you're on the y-axis, and as I get closer and closer to y is 0, then what is my value becoming? This is along the x-axis. This is along the line x equals y, which is here, right here, in the going in, right? And y equals x squared, which would be parabola shaped. And this is y equals mx, which could be m could be any value like y equals 2x or y equals 3x, and m just being the slope, any value there. So just to kind of show you, and so there, so if I use this path, so I'm going to call, and in the book they call the paths like C1, so path C1. And so, but I usually just say, okay, I'm going to go along this path. So my path is going to be x equals 0. I'm just going to use that one as my one right now. So what I would do then, and notice that if x is 0, that is going to go to where I'm going, because I see that x is 0 here, so I'm okay. So it wouldn't be okay for me to say x is 1, because this x is getting close to 0. And so then I would be looking at the limit as y goes to 0. See, that kind of cuts out one of the pieces, which is kind of nice. And everywhere I see x, I want to put in 0. So this is 0 squared divided by 0 squared plus y squared. So this is plus 2. Sorry, plus 2. I put the plus 2 there just to lift it off the axis. And so so that for the drawing, for the looking at it from the drawing perspective. So this part over here is the limit as y goes to 0. Now this 0 divided by anything that's non-zero is equal to 0. So this is 0 plus 2. So this is equal to 2. I was going to say 0, but 0 plus 2 is 2. So my limit here is 2. And that was path x equals 0. So I was going along the path x equals 0, which is another a way of saying I was going along the y-axis. So as I went along the y-axis, the height down here, the height was right here. As I got closer and closer, the height was at a height of 2 is what it was. Okay, so I'm going to try another path. And if I get 2 as the limit, then I haven't helped myself. And if I get something other than 2, then I can say, well, I found 2 paths that disagree with each other on the limit, and I can say the limit doesn't exist. So, and then I get path after path after path that say that the limit is 2. If that happens, then I will try to think of a different way of proving that the limit is 2, because I can't prove it's 2 by not finding a contradiction. That's not a way. So if I say y is 0, that's another favorite path. And notice that as I go along, y is getting closer to 0. So that's good. And so this would be the limit as x goes to 0. And everywhere I see y, I'm going to put in 0. So this can be x squared over x squared plus 0 squared plus 2. So this is the limit, and I don't know why I sometimes do cursive limit and why I sometimes do print limit. And I try to be consistent, but I'm not. I know that. But now x squared plus 0 is x squared, and x squared divided by x squared is equal to 1. So this is 1 plus 2, which is 3. And so that means that now when you're going along y equals 0, that's the x-axis. And so that's this axis right here. So if I'm going along the x-axis and I'm getting closer and closer to 0, my height is getting closer and closer. So this is parallel, right? Parallel to this is along the x-axis, along the x-axis. I'm getting closer and closer up there to 3 is what I'm getting closer and closer to. So that's kind of the story on that. I have also have this one graphed, and I will get on my computer screen here, and I have graphed this one. So here it is. And so I just changed this problem from the problem out of a textbook that I saw to be +2 because it was so close on the axis so that you couldn't see it on the axis. But you can kind of see that this one's got a weird crinkle in it. The surface does. And so as we get closer to a point, which the point was 0, 0, which is the center right here, right? The height, which is the z value, the output, so as the x and the y get closer and closer to 0, the height is getting closer to different values depending on where you're coming in from because of that weird crease kind of thing going up there at the top. I don't know if that has a formal name or not. Now, I almost went back to paper view without going back to paper view. Now, this is enough, and I'm done. So I could say I'm done right here, and because these two paths are not the same, I can say the limit does not exist. The limit is D and E, and that could be my answer. And this is my reasoning over here. Now, I just want to show you that this one, y equals mx, would have also worked to show it and been quite clever at showing it as well. And so if I'm, just FYI, so this is overkill. This is too much. I don't know what you want to say. I've already solved the problem and know that it does not exist, but I want to show you that I could have done something else as well. So if I would have used this path, y equals mx, then I want you to see that this is going to 0, 0. So as x gets close to 0, then m times 0 is y, and that's getting close to 0 as well. So this could be going close to 0, 0. So I couldn't put +1 here because then as x gets close to 0, then that would make 0 here, and then y would be getting close to 1, which it's not. It's getting close to 0. But this will be something helpful that we'll need on another one, that idea. And so everywhere I see y, I'm going to put mx is what I'm going to do. And so I'm going to have the limit, and as x goes to 0, and I have x squared, and everywhere I see y, I'm going to put mx. So when the dust clears here, I have the limit as x goes to 0, and that's going to be x squared over, I'm going to x squared plus m squared x squared. Is that okay? And I'm going to have to go right here too. Some more. Limit as x goes to 0. And then I'm going to have x squared, and I'm going to factor out an x squared, and I'm going to have 1 plus m squared, like that, right? And then now the x squares cancel out. Limit as x goes to 0. The x squares cancel out, so this is 1 over 1 plus m squared, which is my answer. 1 over, because there's no x's in there, right? 1 over m squared. But here's the deal, is that for different values of m, right? So there's different lines, y equals 2x, right? So that's going in on a line y equals 2x. Then the slope, the height, not the slope, excuse me, the height, slope is 2 here on my line, but m is the slope. But my limit, so that would be my z value, or my height would be at 1/5. But if I was going in on the path y equals 3x, then 3 squared is 9, and I would get 1/10, right? And so So this actually shows that it's a different limit for, there's infinitely many different heights depending on what path I use on this thing. So it's got a really weird crease kind of going on it. This would have been enough to show that it does not exist, because when I use this path, I get one height, and when I use this path, I get another height. Just so that you know, when you go in your book and you look at this, that this is showing that actually infinitely many different paths have infinitely many different values for their limit. They're supposed to be all the same, and it's not. Okay, so we have another example. I guess I could eat a few of my Cheerios here with my chocolate chips. Pretty good. Not bad. Could be worse. Okay. So it says here, find the limit if it exists or show it doesn't exist. And so if I substitute in there, just to make sure, if I substitute in 1 and 0, that's 0, that's 0. So this is 0 minus 0, which is 0. I got so excited here that I didn't show that this was 0 over 0 there to start off with, right? Did you guys notice that? And I'm really sorry that I didn't. But as x goes to 0 and y goes to 0. But I got so excited because I saw that, hey, the hint is to look at these paths. And then I forgot to show that, well, I should have made sure that, when I plugged in. So here, this is 1 squared, that's 0 squared. So this is 1 plus 0. And then that's minus 2, and then plus 1. So down here is also 0, right? Because x is getting close to 1. Okay. So I'm not sure that I could factor that, particularly the bottom. The top looks like it has a common factor of y, but definitely there's not a common factor of y in the denominator. So that makes me start suspecting, that I can't factor it. I don't know that I can multiply by the conjugate. I don't know what I could do. And so now what I'm hoping to do is I'm hoping to show that if I use some different paths, that I would get a different answer. And so that's going to be my strategy. And so good paths to go along are like x equals 1, because that's where x is getting close to. So if I try that path, so if I go along a path, x equals 1 as my path, then that would mean everywhere I have x, I'm going to be putting in 1. And so this is going to be the limit as y goes to 0. And then everywhere I see x, I'm going to be putting in 1. So this is going to be 2y minus 2y divided by, and then x's are 1s. So this is 1 plus y squared minus 2 plus 1. So this is the limit as y goes to 0. The numerator is 0. And the denominator is y squared. Now 0 divided by y squared is equal to 0. So this is the limit as y goes to 0 of 0, which is 0. So we have that. Now, if we can find another path, right? This was going to x is 1, y is 0. X is 1, y is 0. If we can find another path that gives us something other than 0 as the output, then we'll be done and we can say the limit doesn't exist. if we find one that gives us 0, then we'll maybe try a few more and see. Now, the other one would be a good one to choose. And now my house is really cold. My house was really hot. Well, I don't know. I was hot. Now I'm cold. Along, and I hope that you're saying, well, why don't you let y be 0? So this would be the limit as x goes to, not 0. Where's x got to go to? X has got to go to 1. So basically, this is a strategy of making them like the limits that we did in Calc 2 and Calc 1, right? This is the kind of limit I used to do. Okay, now everywhere I see y, I'm putting in 0. So in the numerator, I have 0 minus 0. And in the denominator, everywhere I see y, I'm putting in 0. I have x squared minus 2x plus 1. And that's the limit as x goes to 1 of 0, which is equal to 0. So this thing right here was no help, right? Because it doesn't prove that the limit is 0, because that's only two paths being the same. It might make me start to feel like the limit is 0, but it's definitely not a proof because there are infinitely many paths to the point 1, 0. And so I just got to maybe find another one is what I have to do, is find another one. So that's what I got to be thinking about now. So one of our other favorite paths, and I just want to show you this, was along y equals x. And I want to show you that this path doesn't make sense, because as x gets close and close and close to 1 on this path, y would be getting close and close to 1 because they're equal to one another. And so this path right here, you cannot use because it is not headed for that point right there. Nope, can't use this. Now, one thing that I would be able to use, so I just wanted to note that, because sometimes people get confused about, well, why not? Well, as x gets close to 1, y is getting close to 1. And if I was going to 1, 1, that would be perfectly okay, but I'm not. And so, and I'm just kind of looking at that. And I don't know if you guys notice that factors as x minus 1 times x minus 1. And that was what I sort of noticed that, and started asking myself, well, if that part right there factors, right? So just looking at what I have down there, because this was when y squared was 0, x squared, can you see what I'm writing? X squared minus 2x plus 1 plus y squared. This is x minus 1 times x minus 1 plus y squared. And so that's what started me along the thought of, well, what if I let that be y? That would be y times y, that'd be y squared. And why that might be helpful is because, well, it wouldn't be 0. And I think it's on the path, right? Check this out. So if I do along the path y equals x minus 1, now as x gets close to 1, close to 1, y gets close to 0, right? That's where I wanted to go. So everywhere I see you could do it either way. You could say everywhere you see y, you're going to put in x minus 1, but you could also say everywhere I see x minus 1, I'm going to put in y. Looking at the numerator here, 2 out, 2y out, because it factors, is x minus 1. Did you guys notice that too? That was the first thing the first time I saw this problem that that I sort of almost noticed. Now you can't factor it and have those cancel because they won't. I haven't done this in such a way that people could be happy with it. I'm going to show you though that it won't. 2xy minus 2y, when I factor that, becomes 2y times x minus y. And then down here, I have x squared minus 2x plus 1 plus y squared, which I could factor here as x minus 1 times x minus 1 plus y squared. And so those x minus 1s won't cancel with one another. It'd be great if they would, but they don't. But I can replace, because I have the x minus 1s, and it's on my path, it's going to my point here, I can replace either y with x minus 1 or all of the x minus 1s with y, all the y's with x minus 1. Your choice on that. Whichever one you want to do, it doesn't matter. And so me looking at it, I think, well, because I have because I factored it so that I can see that all of the x's are involved in x minus 1, I might as well replace them with y's. So how this will look as the limit. Now I'm going to tell you where my limit is going in just a second because it'll make it easier for me. So I'm going to put this as y. So this is 2y times y, right? I'll put parentheses around it if you want, right? Because I replaced it right there. And then down here, y times y plus y squared. And now it's pretty clear that all I have left in here is y's. So where does y need to be going? Y needs to be going to 0. So this is this path. I'm going to circle this and have this be here. Okay, so this is the limit as y goes to 0 of 2y squared over, and then in the denominator here, y squared plus y squared is 2y squared. So this is the limit as y goes to 0 of 1, which is equal to 1. And now we have done something that will be helpful because we have, going along one path here, x equals 1, we have a limit of 0. And here along this path, which is y equals x minus 1, we got to 1, a different height. And so because of these two things, we can say, so thus, the limit does not exist. So that's the two-path approach. It's only helpful when the limit doesn't exist, because you can then show that two paths have a different limit. And so anyway, so that's the only time it's helpful. If you want to try this by going and replacing all the y's with x minus 1 and then letting x go to 1, you'll get the same result. And you certainly can. That'd be great. Okay, so we have one here. And their hint is to use the squeeze theorem, which I don't know if you guys remember the squeeze theorem from Calc 1, but it can be kind of tricky to use the squeeze theorem. So we're going to give it a try. And they've given us some hints, and so they've given us the hint that 5x squared divided by x squared equals 5. And you might be saying, Oh yeah, that's true. And then what they did is they said, what if I added something to the denominator, y squared, which is positive? And so thus they have made the denominator bigger. And so, but they left the numerator the same. And so I just want to show you on my calculator what would happen here if I left my numerator the same. I'm just going to pick an arbitrary value for my numerator, and I'm just going to leave it the same. And I just want you to see what happens when my denominator gets bigger. And in fact, we'll say that x squared just stays the same. So this is 5, and we'll just say x squared is a constant value of 2, just for yucks, 2, right? Plus, and then the y squared. So let me start off with here. See, I was at 5 there, but if I add y squared, so I add some value, you can even put squares here if that made you happy. Does that make you happier to have squares? Why couldn't I do exponent 2? I hope I have an exponent 2. So I'm getting 5. And now if I add some y squared, no matter what y squared is, that's 2.5, right? 2.5. No matter what y squares is, maybe I'll let it be 9. 14 over 17, that's considerably under 1, right? There's a 0.235. No matter what, it's getting smaller, right? And so that's all they're saying. If you add something to the denominator, that's getting smaller. Now, if y was 0, because it didn't put any value on y, but if y was 0, then I'd just be getting 5. So that thus the equals. Now, if you're thinking, well, why did you add y squared? It's because look at how close we are to what we have for our limit. And the other thing that I can say about this, so I can say that this is for every value of x, for every value of y, not just these particular values here, that this is smaller than or equal to 5. But the other thing I can say about this, because 5 is positive, x squared is positive, x squared in the denominator is positive, y squared is positive, and I'm adding them, I can always say that this is non-negative. Would you guys agree with that? And so thus, I have this. And I'm starting to build the squeeze theorem, right? The squeeze theorem is you get something trapped between. Now, the only thing I'm missing is y right there. And if I multiply by y, and y could be positive or negative, then there's 2 ways that I can handle this. I can handle it with 2 cases, because if y is negative, you need to flip the symbols. And if y is positive, then you don't flip the symbols. And so that's one way of handling the problem, is to do it in 2 cases. If y is positive and y is negative, and show that they're equal to one another. And so the other way of doing it, and this is how they do it in your book, is to multiply by the absolute value of y. And because then I'm guaranteed that it is positive. But I had a really hard time wrapping my head around why that would be okay. And so it wasn't until I just simply until I said this, that I'm going to multiply here by y, and I'm going to have y be greater than or equal to 0. So that's positive. And so when I do that, I don't flip the symbol. And so here I'm going to get 0 times y is 0. And then times y is, and no flip of the symbol, so 5x squared over x squared plus y squared. Same symbol, and then 5 times y. And now if I do the limit of all three sides, that's what I want to do now, right? So I want to do the limit as x, y goes to 0, 0 of 0. So when I do that, well, that's 0. And this is the limit as 5x squared y. I'm going to put a little plus on the y. I'm going to make it more clear that I put a little plus on the y because I'm keeping y positive. What x can be anything at once. Party on x. My gosh, my handwriting is so, I'm trying to fit it in there because now I'm writing twice as much as what I had. Or this is the limit as x, y goes to 0, 0 plus of 0. This is the limit as x, y goes to 0, 0 plus of 5x squared y over x squared plus y squared. This is the limit as x, y. That's a lot to write. 0, 0 plus, but it's a proof. So I should be kind of, writing out all of the pieces. So this is definitely going to 0. This is what I'm trying to find. And this, as y goes to 0, is going to 0. So this is being squeezed to 0. Versus if I multiply by y, but y is less than or equal to 0. That means it's negative, and I'll have to flip it good. So when I multiply here by y, I get 0. When I multiply here by y, I get 5x squared y over x squared plus y squared. When I multiply, and notice I flip the symbol because it's negative, here I get 5y. So when I rewrite this around, this is 5y, because I like to keep it in order. Right? And then now I'm going to do that same thing with the limit, except for instead of going to 0 plus, it's going to be going to 0 minus for the y. So this is the limit as xy goes to 0, 0 minus. So as y gets close to 0, but a little bit smaller than 0, this is going to 0. And the limit, and I'm going to just be a little bit lazy and not write what it's going to since it's going to the same place. And this is the limit and same place of 0. And do you guys agree with me? And this is the limit as, and I'm going to write it here because I don't want to be, I want to make sure everyone gets what I just did. I like this better. than the absolute value way, because I have to tell you, they have it in your book with the absolute value. But it took me the longest time to wrap my head around why it would be the same. And now I have proved that the left and the right are going to the same spot, which is 0. And so since they're the same, I have proved that the limit as x, y goes to 0, 0 of my function that I have here, right, is equal to 0 using the squeeze theorem. And I feel very clever to have done that. Okay, so we did a good job. If you want to see the absolute value, go check it out in your book. And I think they both work excellently. Okay, some limits can be showed using polar coordinates. And so this is one, and they give me the hint, use the polar coordinates. So we'll give a try to that. So right now it's in the indeterminate form, because as I get close to 0, 0, this is getting really, really close to 0 here. And then the natural log of 0, I don't know if you guys remember the picture of natural log, but this is natural log. And what we have, this is y equals the natural log of x. Forgive me, it's, but I'm now saying that this part in here is just x, just for a second, just to prove to you that if this is getting close to 0, I'm going towards negative infinity, right? And so this is an indeterminate form, 0 times negative infinity. And there are times when 0 times negative infinity is equal to 0. And there's times when 0 times negative infinity is equal to negative infinity. And there's times when 0 times negative infinity is equal to negative 57. You don't know what it's going to be until you start working with it. Although you've probably seen this story enough times to make a good guess where it's going. And so anyway, we'll give a try to it. Now, how you use polar is that, I don't know if you guys remember, but I hope you do, that in polar, x squared plus y squared equals r squared. And so, so that's going to work out real good for us, because then we're going to have the limit, and I'm shivering, r squared, natural log, I hope I'm not getting sick, r squared, like that. So help me figure out then where my limit would be going to, x and y. So are you guys thinking about it? So x is getting closer to 0, y is getting closer to 0. So what's r getting closer to? I agree. It's getting closer to 0. Now, one more thing, just real quick, because this is going to be a little bit important to us too. Just thinking about this graph over here. No matter if x is positive or negative, when you square it, it's positive. And if y is positive or negative, when you square it, it's positive. So really, r is getting closer to 0, but we want to keep it on the positive side there. Okay, so now we still have that indeterminate form, but now we're going to be able to do some things. You probably remember that you can put that in the denominator. So this is the limit as r goes to 0 from the positive side of the natural log of r squared divided by r to the negative 2. And now what we have is this numerator is going to negative infinity, And as this gets close, now remember that r to the -2 is the same as 1 over r to the second. I just wrote it as r to the -2 because that would be cute. And as this gets close to 0, 1 over getting close to 0 is infinity. And that means that we can now use L'Hopital's rule. And so that's is that Calc 2? We didn't do L'Hopital's rule in Calc 1. And I abbreviate L'Hopital's rule LH. That's because I'm not a very good speller, and that's quick and easy to do. And so now I got to do these, the derivative of the numerator and the derivative of the denominator separately, no quotient rule on L'Hopital's rule. So this is 1 over r squared, and then chain rule times 2r. And then this is -2r to the -3, right? If I did that right. And so when the dust clears here, I'm going to erase this so that I can have some room for the dust to clear. I'm going to have, so I have not taken my limit yet, so I should still be writing my limit, and so should you. In the numerator here, maybe I would be happier. How's that going to cancel? That's going to be 2 over r. And in the denominator, I have -2 over r to the third. So that this is 2 over r times r to the third over -2. And so this thing is going to become, just doing a little algebra here, it's going to become negative r to the second, I think. That's what I think it's going to become. What do you think it's going to become? And then we're going to get, when you go to 0, we're going to get 0. And so, thus, the limit as x, y goes to 0, 0 of this thing is going to 0. And there's my reasoning for that. A lovely job on that. Freezing to death we were, but we did it anyway. I moved this one down here to example 6, but I meant to remove it because it's too many examples. But I'm going to go ahead and do it because it's too many examples. But if you're bored of them, just fast forward a little. Okay. If I put in 0 for x, sine of 0, 0. So this is 0 in the numerator and definitely 0 in the denominator. And I can't split the denominator apart. Boy, that would be nice if I could. And I don't see a way of doing any paths. I mean, I don't see a way of doing any factoring or any multiplying by the conjugate. That's the one I wanted to put on here. I think I have that one on the lab. I hope I do. And so thinking about some of our favorite paths, like if I let x, if I go along, x is 0. So this is going to become the limit as y goes to 0. So x is 0 is going to be sine squared y over 0 for x, so over y squared. And, oh, I guess I did want to keep this in here. I went back and forth on it. But this is, I just want to write it this way, the limit as y goes to 0. And I want to write it this way so that you guys know that I'm not just faking, that I know what it is. Because I know, and then when you have the square out here, the next property that we learned on limits is that square could go out here. And for sure, we know by theorem 7, I call it. Stewart Book didn't call it a name though, but we know that this is equal to 1. So this is equal to 1 squared, which is 1. And that's along this path. If I can pick another path that gives me a different value, then I'll be able to say the limit doesn't exist. And so my other favorite path would be y equals 0. So that would be the limit as x goes to 0. So y is going to be 0. So sine of 0 is 0, and then square root is 0 is squared. So this is x squared over 2x squared, right? Because that's 0. So this is the limit as x goes to 0 of half, which is half. And then boom, those are not equal to one another, right? So thus, the limit does not exist. Limit doesn't exist. So we did a lovely job on that. Okay, what else is there? Hopefully not another limit problem. You never know though. Limit problem after limit problem. There's a little bit of continuity here. And then we can go to bed. What time is it? Oh, it's pretty late. No wonder Kevin was saying, what are you doing? Now I get it. Okay. So f is continuous at a point if f is defined at a point, if the limit exists, so that's why it's in the limit section, and if they're equal to one another. Determine the set of points of which the function is continuous. And I don't know if you guys remember that there's certain functions that are continuous on their domain. So it's just a matter of finding the domain, and polynomials, rational functions, root functions, trig functions, exponential functions, logarithmic functions. That's the one I got right here. So I don't have to use the continuity checklist on this because it's one of my friends, and I can say that it's continuous on its domain. And so, because it's a logarithmic function, so it's continuous on its domain. And so what is its domain? Well, its domain is x minus y has to be greater than 0. And you can write that, I guess you can leave it like that if you like, it would be okay. And so it's continuous at these points, the set of x, y, such that x minus y is greater than 0. There's other ways of writing that. Of course, you could put the y on the other side. You could put the x on the other side, multiply by -1 and flip it. Whatever makes you happiest. Depending on what you're going to do with it next, I guess, is what you care about. So it's continuous on its domain. This is its domain, so this is where it's continuous. Determine the set of points for which the function is continuous. This is example 8. And, well, this is rational. And so I guess it's continuous on its domain too. Why did I put the continuity checklist there and then not have any, like piecewise defined? You have to use the continuity checklist for sure. continuous on its domain because it's rational. And its domain is when x squared plus y squared plus z squared minus 4 is not equal to 0. And that means that x squared plus y squared plus z squared is not equal to 4. And well, that's where it's continuous. So it's continuous when the set of x, y, z such that x squared plus y squared plus z squared is not equal to 4. So I think that means that this thing that's a sphere, right, with radius 2. So that means that it's continuous except for on the sphere of radius 2. Okay, I'm tired. It's bedtime. I hope I push record. I always say that at this point. Okay, let me see here. Bye. Good night.